Today we're looking at LeetCode 3121, count the number of special characters 2. And this problem is interesting because the statement sounds simple at first, but the condition it gives you is actually very strict. We are given a string containing lowercase and uppercase English letters. And a character is considered special if the lowercase version exists and the uppercase version also exists. But then the problem adds one more condition. Every lowercase occurrence must appear before the first uppercase occurrence. And that one sentence completely changes the problem. Because now this is no longer just about checking whether both versions exist. Now, we also care about order. And more specifically, we care about whether the lowercase letters stay completely to the left of the uppercase letters. Let's slow down and really understand what that means. Suppose the word is A, uppercase A. This is valid, because all lowercase a characters appear before the first uppercase A. But now imagine A, uppercase A. Suddenly this becomes invalid. And the reason is subtle. The moment we saw uppercase A, the lowercase section for that character was supposed to be finished forever, but another lowercase a appeared afterward. So the ordering rule broke, and once that happens, that character can never become special again. Now this immediately gives us an important observation. This problem is not asking how many lowercase and uppercase pairs exist. It's asking, did the ordering remain clean throughout the entire scan? And that changes how we think about the solution. Because whenever order matters in a string problem, we usually need some kind of state tracking while moving left to right. Not after, during the scan itself. Now, before jumping into the optimized approach, let's walk through the example very carefully. The word is A, uppercase A, B, C, uppercase B, uppercase C. And while scanning this string, we are going to maintain three things. First, the latest position where we saw each lowercase letter. Second, the first position where we saw each uppercase letter. And third, a set of invalid characters, meaning characters whose ordering rule has already been broken. Now at the beginning, everything is empty. No lowercase positions, no uppercase positions, no invalid characters. We start at index 0. The character is lowercase a, so we record that the latest lowercase a appeared at index 0. Nothing strange yet, we still have not seen uppercase a. Now we move to index 1. Again, we see lowercase a, so we simply update the latest lowercase position of a from 0 to 1. Still valid, still clean. Now we move to index 2. This time we see uppercase a, and this is important. We record the first uppercase a position as index 2, not the latest uppercase position, the first one, because the problem specifically cares about whether lowercase letters appear before the first uppercase occurrence. So once this boundary gets established, it becomes permanent. Now move to index 3. We see lowercase b, so we record lowercase b at index 3. No uppercase b has appeared yet, so everything is still valid. Index 4 is lowercase c. Same idea. We record lowercase c at index 4, still clean. Now index 5 gives us uppercase b, so we lock in the first uppercase b position at index 5, and then index 6 gives us uppercase c, so we lock in uppercase c at index 6. Now the scan is complete, and notice something interesting. At no point did we see a lowercase letter after its uppercase version had already appeared. That means nothing became invalid. And now the final step becomes very natural. We simply check which characters satisfy all three conditions. The lowercase version exists, the uppercase version exists, and the character was never marked invalid. For A, the latest lowercase position is 1. The first uppercase position is 2, so lowercase a appeared before uppercase a, valid. For B, lowercase b appeared at index 3, uppercase b appeared at index 5, also valid. For C, lowercase c appeared at index 4. Uppercase c appeared at index 6, again valid. So the answer becomes 3. And hopefully now the structure of the solution starts feeling inevitable. Because once you realize the problem is fundamentally about preserving ordering while scanning left to right, you naturally arrive at state tracking. Now let's talk about the actual logic of the algorithm. As we move through the string one character at a time, every lowercase character updates its latest lowercase position. Because if another lowercase occurrence appears later, that newer position matters more. But uppercase characters behave differently. For uppercase letters, we only care about the first occurrence, because that first uppercase character acts like a wall. Everything lowercase must stay before it. So once we record that position, we never overwrite it again. And now comes the key observation in the whole problem. Whenever we encounter a lowercase character, we immediately ask, have we already seen the uppercase version earlier? If the answer is yes, then the ordering rule has already been broken, which means this character becomes permanently invalid. And that word permanently is important, because no future character can repair the ordering afterward. Once lowercase appears after uppercase, the damage is done. Now think about how efficient this is. We never rescan the string. We never compare every pair manually. We never do nested loops. We just maintain a live picture of the string while moving from left to right exactly once. And that is why the solution runs in linear time. One pass through the string, constant work per character. Now there's also a subtle implementation detail that's easy to miss. For uppercase letters, we must only store the first occurrence, not the latest one. Because imagine, lowercase a, uppercase A, uppercase A. The boundary that matters is still the first uppercase A, not the later one. So if we overwrite that position accidentally, the logic breaks. And similarly, once a character becomes invalid, we never remove it from the invalid set, because the ordering rule is global, not local. Now, once the scan finishes, counting the answer becomes straightforward. We iterate through the lowercase characters we tracked. And for each one, we check, does the uppercase version exist? And was this character never marked invalid? If both conditions hold, then this character contributes 1 to the answer. And that's really the whole solution. Not complicated data structures, not advanced algorithms, just careful observation about what information actually matters while scanning the string. And honestly, this is the kind of medium problem that becomes much easier once you stop thinking about characters and start thinking about state transitions. Because every character is really just changing the status of that letter, lowercase seen, uppercase boundary established, or ordering violated. And once you see the problem that way, the implementation almost writes itself. Anyway, that's the full idea for LeetCode 3121. If this explanation helped you see the intuition more clearly, do subscribe because I'm trying to make these problems feel understandable instead of just memorized. And if there's a problem you struggled with recently, leave it down in the comments. There's a good chance someone else got stuck on the exact same part. Thanks for watching. Peace out.